Alright guys, welcome back to another LeetCode tutorial. Today's problem is called prison cells after n days. So the problem description is like very wordy and a little bit confusing, but I'll just try to summarize like pretty much what they're saying. So essentially what they're saying is like they're giving us some input, and the input is essentially just a row of prison cells. So if you count, there's actually 8 prison cells in this one row, right? So that's never going to change. There's always going to be 8 prison cells in any single row that they give us. And this n here is the number of days that have passed, we can say. So essentially our task is like, given this row of prison cells and also given like these 2 rules, they want to know like, what is our cell going to look like on the 7th day, essentially is like what they're saying. So like they summarize it down below as well. Like if you can see at day 0, the prison cell hasn't changed yet because that's our initial state. But now if you look at day 1, it has changed a little, and we need to like ask ourselves why. So if you look at day 0 here, and you look at our 2 rules, essentially a cell becomes a 1 if its 2 neighbors are 1s. And it also becomes a 1 if its 2 neighbors are 0s. So if you look at this first cell here, right, no matter what day it is, this cell is always going to be a 0 because like it only has 1 neighbor. So it's always going to be a 0 on the upcoming days. And if you look at the last cell as well, 1 neighbor, so it's just going to become a 0 for like the rest of the days. And then if you look at this 0 right here, it turns into a 1 because both of its neighbors are occupied. So that pattern just kind of continues as we go along. Of course, this one turned into a 0 because its neighbors are different. Same with this guy here, different neighbors, so it turned into a 0. And essentially that pattern just keeps continuing. And on the 7th day, this is what we have. So like for the brute force approach, we're going to need an extra array to kind of store our current state, and we'll need a helper function as well to populate that array. And as you guys will see with the brute force solution, for small input sizes it'll work just fine, but if you note down here below, kind of the kicker is like n could be huge, so the brute force solution will not work for large input sizes. Alright guys, so essentially this is what our brute force solution will look like. Essentially what we're doing is we're iterating all the way through n, and at each iteration we have this next day helper function that will pretty much apply these 2 rules. So if we ever are at a cell that has 2 adjacent neighbors that are the same, we'll make this current cell occupied, otherwise it'll become vacant. So as you're going to see right here, it'll work for a small input size. So when our input is 7, of course it'll have like no problem at all. But as you will see shortly, it's just going to completely time out. Alright, yeah, so as you guys can see with this brute force solution, time limit exceeded. That tells us that this solution is just way too slow. And we need to understand why. So the reason that this is being so slow is because this n can be huge, like 10 to the 9th, right? We're going to be iterating an array of length 8 for potentially like 10 to the 9th number of times. So that's where the issue is. I'm going to show you guys on the whiteboard how we can optimize this solution and how we can get a much faster approach. Alright guys, so we know our brute force algorithm is way too slow. Now we need to ask ourselves what observations can we make to make our algorithm faster. So we actually need to come to the realization that like for large input sizes, maybe like 1 million, how do we avoid doing 1 million different iterations? And this is how. So first you need to realize that like each cell can either be a 0 or a 1, occupied or vacant. And we also need to realize that at any given day, the number of cells is not changing. The number of cells will always be 8. So we know that for each cell we have 2 states, and we know that we have a total of 8 cells. So to answer our question of how many combinations are possible, we know the answer is 2 to the 8th, which is essentially 256. So that tells us that there's 256 total combinations. But that's actually kind of misleading because if you think about it, at our first cell and our last cell on any given day, right, these guys will always be 0 no matter what, because they only have at most one neighbor, right? Just one neighbor. So we know that the first cell and the last cell will always be 0. So rather than actually 2 to the 8th, we can bring this down to 2 to the 6th. So we know 2 to the 6th is 64. So 64 total combinations. Even this number is a little misleading because, because of our rule that, if you're in between 2 cells that are the same, you become occupied, otherwise you become vacant, right? Because of that rule, there's actually a lot less combinations than this 64 here. So we know, if we know this, that's very important insight. So if we're given some input, I actually don't really care what the input is. It can be anything. But if this is our input, we need to notice something very particular about this. So look at day 1 and look at day 15. Can you see that day 1 and day 15 are the exact same? Okay, well, this tells us that from day 1 to day 15, we do in fact have a cycle, okay? And this also tells us that our cycle length, it will be 14. So after every 14 days, the results will just keep on repeating. And so now that we know our cycle length, for any n number of days, we can solve our problem and return back the status of our array after n days. So we know we're good. Alright guys, so in order to figure out why cycles can help us solve this problem, I want to introduce you to this smaller example. So let's say I give you a list of letters, A, B, and C, and for this list of letters, let's say that these letters have to follow each other in a certain way. So if we kind of write out the sequence, first A would come, and then for every A that we write, immediately it has to be followed by a B, and then a B has to be followed by a C, and then after a C we have to write an A, and then after an A we have to write a B, and I think you can get the idea here. So, we're given these letters, we're given these patterns, and the pattern dictates how we can actually write these letters out. So now that we know how the sequence looks like, let's say I asked you, what is the 17th letter in the sequence? By the end of this example, you'll be able to tell me this answer within a couple seconds. But for now, since we don't know how the cycle will help us, we're just going to naively write out the sequence. So A comes at the 0th position. After we write an A, we have to write a B. So B is 1, C would be 2, and then we're just going to keep writing this out. So as you guys can see, if we just manually write out the sequence, we see that our 17th letter is C, and we're good. So the 17th letter in this case would just be C. But remember, I told you that we should be able to answer this question within a couple seconds. Writing out this sequence takes a very long time. So what's a trick we can use to just quickly get this answer? So in order to realize this solution, you have to first look at the first 3 letters here. We have A, B, C. And then immediately after the C, we have another A, B, C. And then another A, B, C. We can see that after every 3 letters, we have a cycle. And in this case, our cycle is of length 3, because we have A, B, C. So if I were to tell you to find me the 17th letter, and we know that our cycle is length 3, we can actually use the mod operation to quickly get our answer. So if we were to quickly do 17 mod 3, we get an answer of 2, right? And originally I told you, I gave you this list of letters. We can write A as 0, we can write B as 1, we could write C as 2. So if you know the length of the cycles, and I'm giving you find the 17th letter, all you have to do is 17 mod 3, you get 2, and what do you know? 2 corresponds to C, and C is also our 17th letter. Now, to show you that this isn't just a coincidence, I want to do one more example. So rather than the 17th, let's say I told you to find the 15th letter. Again, you can do this in seconds. You want to find the 15th letter? Cool. You know that there's a cycle after every 3 letters? Awesome. All I got to do is 15 mod 3. I get a quick answer of 0, and what do you know? 0 responds to A, and I know quickly that the 15th letter must be A. And just to double check, we do see that in fact the 15th letter is A. So we can use this trick, now that if we want to think about the original problem, we can use the same trick on the original problem at hand. All we got to do is figure out the cycle length, and if we know the particular cycle length, rather than 15th letter here in our problem, this would be like n days, right? So that's why I kind of told you it's like the same thing. So if they give us any number of days, like I don't care how many, and we know our cycle length, we can figure out what the state will be after n days, no matter what, very easily, and we will not have to run this thing for potentially 1 million iterations. Alright, you guys, so now that we finally know how to solve the problem, we're going to get right into the code. So for this next day function, we actually still need this guy to essentially simulate these 2 rules, So we're still going to keep this next day function to figure out what the next day will be. But the prison after n days function will be entirely different. So, as I said before, we actually need some way of detecting the cycle, and to detect the cycle, we're essentially going to use a hash set. And the hash set will contain strings because it'll just be an easy way to store our the state of our cells array. And once we have our hash set, we need some way of keeping track of the loop length. So I'm going to initialize that to 0. And now that we have these 2, we can actually begin our iteration. Alright guys, so you might be saying like, why are we still going to n if n could potentially be like very large? So if you know that our cycles happen after every 14 days, you'll see that like for all small inputs, we'll just iterate over the entire days. But for anything greater than 14, right, we would have found our cycle already, and we wouldn't even come close to n iterations, because we would find our cycle and we would just return the remainder. So we know we're good. And we're actually going to need an array to store the results of our next day. So we'll just call this guy next day. Pass in our cells. And after we have this updated array, we actually need to convert it to a string. So string equals next, actually it's going to be arrays.toString, and we're just going to pass in next day. So we now have a string representation of our updated array after the rules were applied. And so now that we have this array, we can say if our set does not contain the string that we're currently looking at, we'll just go ahead and we'll add it to our set. So add that guy in, and we'll also increase our loop length because we know that if we see a fresh array, there's no possible way that we have detected the cycle just yet. Otherwise, if we actually have detected the cycle, we want to calculate our remainder. It's going to be equal to n mod loop length. And this is the exact same thing that we did in our previous examples. We're just figuring out like what our remainder is once we know the loop length and we know how big n is. It'll be very simple to just calculate our remainder with the simple mod operation. Right, so we know our remainder, so essentially we're just going to introduce a new variable j, so that equals 0 as long as j is less than our remainder, of course, j++, and we're going to say in this particular block, all we're saying is like, if we know our remainder, let's say our remainder is like 2 or something, we know that like our answer will lie in the next 2 iterations. If our remainder is like 1, we know our remainder will be in the very next iteration, so on and so forth. So again, we're going to use this next day function. We're going to pass in our cells. And so once we have this updated cells array, updated according to like whatever our remainder is, we can actually just go ahead and return the cells and just break out of the loop early. Otherwise, you know, if the entire like loop runs like all the way through, we know that n was probably like less than 14, which in that case we can just return the cells, and we should be good. So let's go ahead and submit just to make sure that we're in good shape. Oh, sorry, extra C in there. Oh, sorry guys, I just realized that we're actually not returning anything, so we want to make sure we return that integer array. Let's run it again. Okay guys, so I just figured we actually need to return an integer array, and we're only passing in 1 parameter here. Okay, so I just figured out, guys, we actually need to return an integer array here, and rather than passing in this current state into our arguments, we're just going to initialize it right here. So that's going to be a new integer array, and it's just going to be the exact same size as our original cells array. Okay guys, so I just keep finding all these errors, but we actually also want to make sure that we set cells equivalent to next day. So I think that should hopefully take care of everything. Alright, looks good so far, so let's go ahead and submit. Alright, and we're good. So to be honest, like for this particular problem, I wouldn't dwell too much on this like speed, this relative speed over here. As long as you kind of like understand like how we used cycles to our advantage, I think that's a lot more valuable than getting a fast runtime here. So because you can take that to other problems beyond this one here. You know, and getting the perfect solution for this isn't too important. So yeah guys, that's how we solve this, and I hope this was helpful. I'll see you in the next one.